Hello everyone and welcome back to the channel. Today we will be discussing a problem called the Great Crystal Bridge Network. It's a very interesting connectivity problem which seems really simple at the start but gets surprisingly difficult. So let's get into it. Here's the problem statement. You have n houses, right, like I have on the picture, and you have m bridges that connect them. So you have sort of like a graph. Now here's the interesting part. For every bridge, besides knowing which which houses it connects, you also know three values. The year that it was built, so year 1, the year that it was destroyed, year 2, and the maximum weight that it can support, a W. So if you imagine you have like a car with some weights, I don't know, let's call it S, you can travel on a bridge if W of that bridge is greater or equal to S. Now you need to answer Q queries. Every query asks you the following question. Could you, in the year Y, travel from cities A to city B using a car of weight W? So this practically means that you can use any bridge with y1 less than or equal to y, so it was built before your travel, y2 greater or equal to y, so it was not destroyed by the time that you're traveling, and w is greater or equal than w of a car, so the bridge can support your weight. And answer to every query is of course only yes or no. That's the problem. So n number of houses is less than or equal than 50,000, and number of edges and number of queries is less than or equal 100,000. Time limit is around 5 seconds. Okay, that's the problem. Now, what I try to teach my students is that you usually cannot solve the problem from the get, right? Just by looking at it. You need to start somewhere, right? If you solve the problem right away, it just means that it's too easy for you. So, a good starting point is to think about the similar problem but simplified, so like a subtask. So what I would do in this case is forget about those y1, y2 and w values and forget about year and weight. Like just forget about time and weight. You just have a graph with n vertices, m edges, and you just have queries of type A and B. So your question is, can you go from A to B? There's two solutions. One is conceptually simpler, but the other one will help us solve the full problem. So I'll start with the simpler one. What you can do is, since the graph doesn't change, you can just pre-calculate stuff. So in this case, you can just break it down into components. So you can start at any node, and using DFS or BFS, you can fill the entire component. So you will mark for every node that it belongs to component number 1. And then you just go through all other nodes, and when you encounter a node that is unvisited, so it's not part of any new component, you give it a new number and you fill the component. So in this case, for example, we found this node, we give it number 2, and then we run the same algorithm. So we fill the entire graph with these components. At the end, if you want to answer any query from A to B, all you need to check is if components of A is equal to components of B. That's it, and time complexity is of m plus q. But there's another way, which might look like an overkill for now, but it will actually really help us. So there's a data structure which is called DSU. You might have heard of it. I think it translates as disjoint set union. Sounds scary, but essentially what it does, I sometimes refer to it as the superglue data structure. It can take two components and it can merge them. It can merge them really fast. In fact, the merge is just of 1. Well, technically it's of inverse Ackermann constant, but we will not talk about it. It's of 1. So you can merge stuff really fast, but you cannot really split stuff. Split is like of n. Even if you need to like split only one node, it might be of n. So we could use this superglue data structure here. What we could do is just initialize it with all nodes being isolated, and then when you get an edge, you merge these two components. So now these two are part of the same component, and these two are part of the same component, and so on. The end result is essentially the same. You just know for every node which component it belongs to. The way you do it in DSU is that there's a function called lead, or like get parent, I call it lead, and it returns you the parent node in a component. It's like the main node in that component. And to answer a query, you just need to compare parents of both nodes in the query. Okay, we solved this problem in like 2 ways, but now it's time to make it harder. So the way we'll do it is by introducing back the weight. So every edge will still be static, it will not go anywhere, but we'll have some maximum weight that it can support. And same goes for queries. Now queries give you the cities A and B, and they give you the weight of the car W. You just need to tell if you can go from city A to city B only using rows that support your car. Now, this one is quite a bit... Now, this subtask is more tricky because you cannot simply separate stuff by components beforehand. Because you can have a case like this. Let's say we have 4 cities like that on a line, and weights are 3, 1, 3. Now, if you're traveling in a car which weighs 1, you can go freely between all of the cities. You can go here, you can go here, like all of them are connected. But if weight of the car is 3, you can only go between these 2 cities and these 2 cities. But you cannot ever cross this edge. And in fact, if weight of the car is greater than 3, then you cannot go anywhere. So we cannot do like simple pre-calculation beforehand and just use the answer. We have to answer each query individually. Now, there's a few ways to do this. One of them involves minimum spanning tree. The idea is you just need to know for every node what is the most restrictive bridge on a path between them. So the most restrictive is the one that has the lowest weight requirement, right? This one is the most restrictive, of course. You could do that with like a minimum spanning tree, so you sort all of the edges by weight in decreasing order, and you just add them one by one. That's one way to do it, but I would like us to use DSU. Here's what we can do. This is an interesting trick. If it's your first time seeing this, you might be a bit blown away. Here's the idea. We are getting Q queries, and we need to answer all of them. But nobody ever said that we have to answer them immediately. What I mean that it doesn't mean that we get one query and then we answer that query. We get second query and then we answer the query, and so on. These are called online queries. Nobody said that we have to answer them right away. What you could do instead is first read all of the queries and then calculate answers and output them in the same order. This is called offline queries. Now, sometimes programs restrict that technique. They only allow you to answer queries online, but this problem is not one of them. So what is the benefit of reading all of the queries beforehand? Like, we still need to answer all of them. Here's a very interesting trick. One thing that I said is that depending on the weight, components are different, but they're actually really similar. Here's what I mean. If let's say we start in this graph and we say that we have weights larger than 3, then our graph will look like this. We will not have any of these edges. They are not available to us. So it will be completely isolated. Now, when you reduce the weight of the car to 3, let's say, you get new edges. So now you get this edge and this edge. This one is still unavailable. So now you can merge these 2 nodes into the same component. As you decrease your weight, when you get to weight equals 1, you get another edge. You get this one in the middle. So now every node is connected. You see what I mean? As the weight of the car decreases, what essentially is happening is just adding more edges to the graph. This means that we can use this powerful superglue data structure, right? Because when you get a new edge and you know that old edges are not getting removed, you're just getting new edges, you can just merge the components in the DSU and then answer the query. So what we can do, we can sort all of the queries by weight. And in descending order. All right? This is what we are going to do. We want to start with the maximum weight because the larger the weight of the car is, the less available edges you have. So let's say we have queries like A, B, and weight is 10, weight is 7, 1, 2, 1. Right? So after sorting them, you'll get query 10, 7, 2, 1, 1. Notice that we can't have two queries with the same weight. All right? Now, what we are going to do, we'll also sort the edges, okay? So let's say we have edge of weight 8, edge of weight 7, another edge of weight 7, edge of weight 3, and an edge of weight 1. So now what we are going to do, we'll keep like a pointer, which will initially point to the first edge. And we'll do the same with queries. So we'll have another pointer here. Now, before answering the query, you first look at you need to add all edges who can support the car in the query, right? Whose weight is greater or equal to the weight in the query, right? So before answering every query, we'll just look at the current edge and we ask ourselves, if its weight is greater or equal than weight of the car in the query, then we can add it and move the pointer. So in this case, query is 10 and edge is 8. So we don't do anything because a bridge of weight 8 cannot support a car of weight 10. So we just answer the query and then we get to the next one. This one has weight equals 7. Okay, we look at the first edge, we see, oh, its weight is actually greater or equal than 7, so it means we can add it. So we add this edge and then we move the pointer down. So we get to the next edge which has weight the same or even less. We check 7 can support 7. Okay, so we add it and move it to the next edge. Again, 7, it works for us. So we add it and we move to the next one. Now 3 is too low for 7. A bridge of capacity 3 cannot support car of weight 7. So we stop here and now we just answer the query. So just answer. Then you move to the next query and so on. You get the idea. Now it's important that we also need to remember the positions of each query, because obviously if you sort them, you forget about their initial position and you want to output them in the same order. So in this case, for example, answers were yes, no, yes, no, yes. But because in the original input they had different order, you need to output yes, no, no, yes, yes. Something like that. The way you do it is really easy. In C++, you just store them in a pair, and the first value will be the weight, and the second one will be the index in the original array. And when you answer the query, you just write to some array, call it ans, and then you output it. And for edges, of course, we just use DSU. When we add an edge, we connect to components in DSU. That's it. This is a really, really simple and really common technique, where you just take all the queries, you sort them in some logical order, and you do some stuff with them. Okay, but now let's try to solve the harder problem. So I would like to introduce back the years, but they are a bit challenging. So let's remove the weights, but introduce the years. Okay, so every edge has some interval where it existed. It was from year 1 to year 2 inclusive. And every query has some year. Okay, now we would like to try the same idea here as in the previous subtask, but we unfortunately cannot. That's because there's no greedy way to sort the edges. What I mean by that is that, for example, let's say I have query with year equal to 4. Well, obviously I want all edges with year 1 less than equal to 4. But now, out of all of those, I want the ones that have year 2 greater equal to 4. Because, for example, we might have an edge which existed from year 1 to year 3. This one doesn't work. It was destroyed before I traveled. What makes this problem harder is that in the previous problem, we could add edges and we knew that we would never remove them. But in this case, as time goes on, as year increases, some edges will get added and some of them will get removed. And we simply cannot do that with DSU. DSU does not support edge removal, but DSU does support a very interesting operation. It's called rollback. Here's the idea. Every time you do a modification, like to any arrays in DSU, you remember that modification. So you remember the value that you changed and the previous value that it had. What this gives you is a possibility to roll back the previous change. So for example, you can add edge from 1 to 3, you can then add edge from 1 to 2, and now you could roll back the previous edge from 1 to, then you could add another edge like 1, 4. Now you cannot remove any edge that you want. For example, in this case, we cannot remove edge 1, 3. Right? This is not a rollback, you're just trying to remove any random edge. So the way that it works is that instead of removing an edge, which is not really possible, you just roll back the changes that you did when you added this edge. So if you imagine your data structure had like a snapshot, so this one is empty, then you added edge 1, 3, then you added edge 1, 2, you essentially just remove the previous snapshot. You go to the previous one before you added that edge. So you have rollbacks. Now, a data structure works in of one time. So in theory, a rollback should also work in of one time. But there's a thing that I didn't tell you. It's actually of one amortized, which means kind of like it works of one on average. In reality, worst case scenario is actually log n. And because of that, rollback is also of log n. Because what might happen is that you add an edge, you get worst case scenario, so it's logarithm of n, then you roll back, logarithm, then you add it again logarithm, and so on. So it does not work in of one time, it works in of log n time. But okay, these rollbacks are cool, but they do not help us solve the problem. You see, if you imagine we have two edges, and one of them exists from year 1 to year 4, and the other one exists from year 2 to year 5. Well, we would first need to add the first edge, then add the second, then remove the first one, and then remove the second. Right? As I said before, it's not possible with rollbacks. You're trying to remove a random edge. But there is a technique to solve that, which is really, really interesting. It's called, actually I don't know what it's called. I think it's called like persistent DSU or something like that. Here's the idea. We will look at the entire timeline. So we'll have like a bunch of edges. So we have edge from this year to this year to this year, and so on. So every segment on this timeline is an edge. It's an interval where it existed. So this is the axis for year. Okay? Now what we will do, we will build a segment tree on this timeline. So if we have, for example, years from 1 to 4, we would build a tree like this. So here, these nodes, for example, this node represents interval for year 1. It just represents year 1. This one represents year 2, this one represents year 3, and so on. But this node, it represents the combined interval of both children. So this one represents interval from 1 to 2, this one from 3 to 4, and this one for entire timeline from 1 to 4. Now, if you know segment tree, you know that it's really good at representing segments with a little number of nodes. What I mean by that is that, for example, let's say we have this segment from 1 to 3. We could represent it with 3 nodes, like this one, and this one. But we could instead take this node, which will represent all values from 1 to 2, and this one, which represents 3 to 3, and you will get the same result. In general, if you have timeline of length n, segment tree can represent any segment with of log n nodes. More specifically, it's 2 times logarithm of n. Alright? Now, here's what we're gonna do. For every node, we will keep a list of edges. Now, what edges will we keep specifically? It's the edges that completely cover this node. So, for example, for this node 1 to 2, it could contain edges that cover segments 1 to 3, for example, or 1 to 4, but it couldn't contain an edge from 2 to 2 because it doesn't cover the entire segment, it only covers a section of it. So we'll keep only the ones that completely cover this node. So with that approach, every edge will be stored in a logarithm of n nodes, of course. That's what we know from segment tree. But let's think about how to actually solve the problem. Let's say we have the segment tree data structure and we try to answer a query for year y. Let's say in this case year equals 2. How would you get all of the edges that we'll have during that year? Well, obviously, if you just go from this node to the parent and to the roots, the only edges that you will see are the ones in these nodes, right? Because every edge that covers this year will either be present here or any of the parents if it covers some larger segment, right? That's the idea. You only need to consider a logarithm of n nodes. But it still might contain a lot of edges, so you cannot just start from the roots, go to the year that we need, and add each edge. It would be too slow. But here's what you can do. You can answer all of the queries in one algorithm. Here's how it's going to work. We will start from the root, right? The root contains all of the edges that cover the entire timeline. So these edges will appear at every query. So what we can do, we can add all of these edges, right? Now we will go to the left. So we want to get the first query, like the query with the smallest year. So we'll go left. Now, when we enter this node, we again do the same thing. We add all of the edges because obviously they will be part of this query, and so on. We do that until we reach the leaf node, which represents year 1. So we have this DSU data structure. This is where we add in all the edges, by the way. So we just take the components, we get the answer, we store it, and we say, okay, very nice. We can answer all queries by year equals 1. But now we want to answer year equal 2. Now here's my question for you. Do we need to start from scratch and just go from roots and add all of these edges again? Well, as you can see, there's a lot of overlap. So for example, we would add all of the edges from this node once again, add all of the edges from this node once again, and so on. There's a lot of overlap. So what we can do instead, we can keep the current data structure, but we can roll back the changes from this node. And now we're in this state again. So the state before we went into the child. So this means we can just directly go into the year 2. We go into that node, we add all of the edges, we answer all of the queries, and now we need to answer year equals 3. So now you know what we're gonna do. We'll roll back every change, and then we go into the right child again. And we follow the same algorithm. Add all of the edges, add all of the edges, answer all of the queries, roll back, go into the right child, add all of the edges, roll back, roll back. This way, you can walk the entire tree and answer all of the queries. But the question now is the time complexity. The way to see why it's fast is to look at every node individually. Let's look at this node. How many times will we add all of its edges? Well, it's obviously only one time, when we enter that node. And we will do one rollback. We will do that when we exit the node, so when we go back to the parent. So in total, for every node, you will do all of 1 operations. Now, to see why that is fast, you think about every edge. We know that every edge is part of logarithm of n nodes. And for each of them, it will be added once and removed once. So for every edge, time complexity is just O of log n. And the total time complexity is just the time complexity for every edge combined, which is simply O of m log n, right? M is the number of edges. It might be a bit confusing. Just think about segment trees, think about adding an edge on a segment, and then just doing a walk on the tree. Alright? This is called DSU with rollbacks or whatever. We sometimes call it persistent DSU because it kind of allows you to add and remove edges. It really doesn't, but it's like a trick that you can use. And this is pretty cool. This is actually a very useful technique. In fact, I think I solved a problem using that technique fairly recently, like during some Code of Forces rounds. I'll leave a link in the description. But now it's time to come back to the final problem. We have year 1, year 2, and then we have weight. And for every query, we have A, B, year, and weight. Now, I would like to use a very common optimization technique. It's really, really common. It's called square root decomposition. Shorthand is SQRT decomposition. Here's the idea. Let's say all of our queries have year equal 1, then year equal 2, and so on. They're like just consecutive values from 1 to Q. We can take this entire timeline, which goes from 1 to Q, and we can split it into blocks of size square root of q. So we'll have a bunch of blocks like this. So the reason why we choose specifically square root of q is such that number of blocks is equal to square root of q, and the size of each block is it's q divided by count, so it's q divided by square root of q. So the size of each block is also square root of q. If you choose any other value, you will either have a larger count or a larger size, which in this case we don't want. Here's the idea that we can do. Every edge is a range. Now we will look at what blocks this edge covers completely. So in this case, it completely covers this block and this block. What this means in practice, it means that this edge appears on every query in that block, right? Because with this decomposition, every query is part of some block. So for example, you have year equal 2, you'll be part of this block. Or let's say you have year equal, I don't know, 8, and you'll be part of this block. So now, if a block is completely covered by an edge, it means that it appears on every query for that block, right? That's the idea. And also, every edge has some leftovers on the left and right. So these are the blocks where it belongs partially. It means that it might appear on some queries, but might not appear on other queries. So in this case, it's this block and this block. Here's what we are going to do. For every block, we will keep two things. One is the DSU, and the other one is a list of edges. DSU will contain all of the edges that completely cover this block. The edges list is just a plain list of all other edges that are partially present in that block. So they appear on some queries but not on other. Now, when you have some query from that block, let's say we have a query here, what we are going to do, we'll take the DSU. So we'll take the component that contains all full edges, and all of the partial edges, we'll add them one by one. So we'll check, is this edge a part of this query? If it is, we add it. If not, we don't add it. So we do those like just in a brute force way. We just add them one by one. Then we answer the query, and then we roll back all of those partial edges, right? Because we want to keep DSU clean. We want it to only contain full edges, edges that completely cover the entire block. So let's say we had a block like this, and it had edges with ranges like this, and like this. So these two edges, I will mark them with blue. They completely cover this block. So they will be part of the DSU. This white edge only partially covers it, so this one will be part of the edges list. Alright? And now when you get a query, for example, let's say we have query here, we just start with DSU because we know that whatever the query in that block is, it has all of the edges that completely cover this block. And then we just go through all edges and add them one by one. So in this case, we will not add this edge, but if query was, for example, here, we would of course add this edge also. After that, after you answer the query, you just roll back all of those changes. And now if you want to introduce weight, it's actually really easy, because this data structure, unlike the previous one, supports adding edges dynamically, right? Because you only contain DSU and list of edges, you will simply sort all of the queries and edges by W, again in descending order. And now at every point when you want to answer a query for a year and a weight, you do the same thing. You first look through all edges which have weight greater or equal to the weight in the query, you add them into this data structure, and then you use the algorithm that I described to find the answer. And that's it. Let's think about the time complexity. So when we are adding an edge, it's really simple, because it's part of at most square root of q blocks. And the addition is of 1 because it's just a DSU. As for partial blocks, it's part of at most 2 blocks partially, and you're just adding them to some list, so like a vector in C++. So this is of 1 also. So the time complexity of adding a single edge is of square root of q. When you want to answer a query, you simply go to the block, you add all of the edges, so I'll say this is of size, you check if components are the same, this is of 1, and then you do rollback, which is also of size. Well, as I said before, it's of size logarithm. So it's of size log n. Now, it might be unclear why this is fast. The idea is you need to look at every partial edge. So let's say this one. You need to ask yourselves, how many times will it be added in the second part? So here. How many times will we need to add this edge manually and then remove it manually, like do the rollback? Well, because of how the queries look like right now, I said the queries go from 1 to q, every block represents at most square root of q queries, right? So for every edge, it's part of 2 partial blocks, and for each of them, it will be part of square root of q queries. So when you do that sum for every edge, you essentially just do square root of q operations. And then, of course, when you multiply by the number of edges, you get of m square root of q. So what this means is that an individual query might be quite slow, but when you do all of them, it will be fast because each edge is only part of square root of q queries. That's the idea. But of course, rollbacks are a bit slow because they multiply the solution by logarithm. Because this you can add stuff in O1 amortize, but you cannot remove stuff in O1. Now we can actually solve this really easily just by not doing any additions to DSU and not doing any rollbacks. Here's the idea. This DSU will only add edges here, like only the full edges. We will never add anything else to it. But how do you find the answer? It's actually really easy. We'll just go through all edges, and instead of creating an edge between 2 nodes, A and B, we'll instead create an edge between components in the DSU. So let's say A is part of component C of A, and B is part of component C of B. So we'll simply create a new graph. And now we just need to check if 2 nodes are connected in this graph. So guess what we can do? Of course, we can use either the DFS algorithm from the start, so just like a flood fill, or we can use another DSU if you really want to. It's like you create a new DSU. But actually DSU doesn't work here. Why? Is because, well, this graph might have a lot of nodes, right? It might have like n nodes, right? How do we know? But it only has size edges, right? Size is the number of partial edges in a block. DSU is of n plus m, but DFS is only of m. You see why that is important here? We usually say that both are linear, but in this case it's really important that DFS doesn't require us to visit every single node. For example, we can have a bunch of other isolated nodes, but we don't care about them. We don't need to check each of them. So this is our algorithm. We'll just go through all the edges. Because we need to somehow merge the results of DSU and these edges, we will use the components from DSU. So when we add an edge, instead of adding an edge between 2 nodes, we effectively add edge between 2 components. And now you need to find whether node A is connected to node B. And of course, remember, because these are not actual nodes, these are components in DSU, A is actually the parent in DSU of A, and B is the parent of B in DSU. That's the idea. Like, you just take their components and see if they are connected. After you do all that, you just discard that graph. Like, we build it in O of M, we find the connected components in O of M, and then we just, I don't know, we just clear it. So O of M means O of size. This means that our final time complexity does not have a logarithm. It's a clean O of M square root of Q. But we didn't solve the problem yet, unfortunately, because as you remember, at the start I made an assumption that all of the queries have consecutive years, like they go from 1 to Q. Who said that has to be the case? I mean, technically all the queries can have like the same year, right? Or they can be all part of the same block. In which case the time complexity completely breaks. Like, the only reason it was fast is because we said that every block has only square root of Q queries. But if it can be up to n, then you can simply get one block which has all of the edges partially, so size equal to O of M, and it has all of the queries. So you get Q queries here, and final time complexity would be Q times M, which is of course too slow. It's a quadratic solution. Now, during the actual competition, I was able to get to this part, and I didn't know how to fix this issue. I simply thought that it's like not a good solution and there's something much more tricky or whatever. But turns out there's like a really simple trick to solve it. And here's the idea. The condition at which the solution works is if every block contains small number of queries, so square root of q queries. But if we split the timeline by fixed sizes, we can get a lot of queries in the same block. So guess what we're going to do? We will not split the timeline by the fixed sizes. We will split it by queries. Let me show you. Let's say I have queries for year 1, or year 1 again, year 4, and year 6. Instead of creating blocks, let's say from 1 to 3 and from 4 to 6, I'll create blocks 1 to 1 and then 4 to 6. Now for edges, W complexity is still the same. Like every edge can be part of at most square root of q blocks, blah blah blah, it will be fast. But now each block has at most, it's not exactly, but at most square root of q queries. And what's interesting, the way that it works is that even if all queries are the same, let's say you have queries 1, 1, 1, 1, 1, 1, you'd create these blocks. And each query is assigned to its own block. So even if they're all equal, each block still has square root of q queries. That's crazy, right? Like, we can have blocks, we can have multiple blocks that have like the same range, which is just kind of weird. That's not what you usually do. And you might think, well, it definitely breaks something when it comes to edges. Like, definitely when you add them, something breaks. Well, no, because the only thing that edges care about is that the total number of blocks is small. In this case, it doesn't matter how we split them, the total number is still square root of q. That's the idea. This is the final solution. You sort all the queries by year, then you split them into blocks. So you assign each query a block, such that each block has at most square root of q queries in it. And then you do the algorithm that we did with the W. We sort queries by W, we sort not only queries but edges. And now when you want to answer some query, you first add all edges who have weight greater or equal to the query. So in this case, it will look something like this. For weight 10, we don't have any edges. For weight 8, we don't have any edges. Now for weight 2, we add this edge. Then we go to the next one, we add this edge. We go to the next one, we add this edge. We go to the next one, we add this edge, we go to the next one. Now we stop, we answer the query, go to the next edge, we add this edge, and go to the next one. Now there's no next edge, so we'll stop adding edges from now on. So we answer this query, then go to the next one, and boom, that's it. Every addition of edge is O of square root of q, because this is how many blocks we have. And now every query is of size, so the number of partial edges. And as we said before, if you look at every edge, it's part of two partial blocks, so you have two partial edges. This means that it's part of two square root of q queries, and in each of them it will contribute one edge. And when you sum this together for all queries, you get O of m times square root of q. That's it. The problem is solved. Now, if you think it's complicated, I advise you to revisit the previous subtasks where we only had years, we only have weights and so on. And if you want to solve this problem, it's actually a bit problematic because this problem is not really publicly accessible. It's part of an ongoing competition, but you can actually just register and participate. And if you want to solve this problem, I'll leave a link to it. If you register for competition, you can simply open the link and upsolve it, alright? And if you have any other ideas, problems, or topics you would like to see on the channel, on this simpler format, you let me know. Also, I'm just starting out this second channel, so I'm not entirely sure how the videos should look like. So if you have any suggestions, please let me know in the comments. I would love to see those. With that being said, thank you all for watching this video. I enjoyed making it quite a lot. This is a very interesting problem. And see you soon.